Enterprise organizations often maintain hundreds of isolated legacy SQL Server 2012 and 2016 deployments, scattered across massive on-premises data centers. Managing these instances requires touching each server individually. These legacy systems are now passing their end-of-support dates. Without standard security patches, any new critical or important vulnerability instantly becomes a regulatory exposure. To stay compliant, organizations must acquire Extended Security Updates, or ESUs. Securing these updates creates a structural problem for database administrators. They must shift from managing distinct instances via local tools like SQL Server Management Studio to governing an entire dispersed estate through a unified cloud interface. Azure Arc acts as a bridge, projecting isolated legacy SQL instances into the Azure control plane. A local agent establishes a secure, outbound HTTPS connection over TCP port 443. With zero inbound firewall rules, it pulls a proxy representation of your databases into Azure. Once connected, Azure Arc delivers extended security updates dynamically on a monthly pay-as-you-go basis. You bypass the traditional requirement of purchasing multi-year volume licenses up front. Extending cloud governance to local hardware creates a new set of architectural dependencies. Navigating these requires precise mastery over 4 specific operational domains to protect existing high availability and security baselines. The most dangerous assumption database administrators make during onboarding is that Azure Arc will automatically push patch files and restart their SQL servers. It does not. This diagram shows the hybrid patching lifecycle, separating entitlement and execution. Your existing infrastructure tooling remains entirely responsible for applying the binary patch payload. Azure Arc merely drops a localized certificate onto the server. That certificate unlocks the payload, allowing Windows Update to proceed. To make this work, you install 2 core components on the host machine, the connected machine agent and the SQL extension. The installation of these specific Arc agents runs in the background. It will not force a server restart or disrupt active workloads. The actual threat to your uptime lies in a hidden operating system prerequisite. This matrix compares the default environment with the deployment requirements. The SQL extension strictly requires .NET Framework 4.7.2 or higher to function. A default Windows Server 2016 installation only ships with version 4.6.2. Before you can even attempt to deploy Azure Arc, your infrastructure team must upgrade the .NET Framework across the legacy estate. This is a major OS-level modification that often requires a planned reboot. Arc does not hijack your existing patching runbooks, it simply entitles them. The immediate risk to your database availability is concentrated in upgrading OS prerequisites before Arc is ever deployed. Once the agent is active, we have to look at the security footprint Arc creates directly inside the local SQL Server instance. By default, the Arc connected machine agent runs under the Windows local system account, needing basic connection rights to execute its tasks. When the SQL extension detects your databases, it automatically elevates the NT Authority system account directly into the sysadmin server role. Arc requires this access to extract deep telemetry for the Azure dashboard and run automated best practices assessments across indexes, configurations, and backups. This automatic escalation immediately triggers alarms during enterprise InfoSec audits. Granting automated sysadmin rights to a local machine account directly violates strict zero-trust hardening baselines. This table compares default security behavior against the required mitigation strategy, deploying the SQL extension in least privilege mode. Instead of relying on the local system account, least privilege mode provisions a dedicated virtual account. It limits access to granular permissions, like view server state, isolating the extension. Achieving cloud visibility does not require abandoning your zero-trust architecture. Enforcing least privilege mode satisfies Azure's telemetry requirements while passing local InfoSec audits. High availability topologies require precise licensing management. Azure Arc enforces strict rules on how disaster recovery nodes operate under its billing structure. Under software assurance or Arc pay-as-you-go policies, you're entitled to run one passive node for high availability and a second passive node for disaster recovery at zero additional licensing cost. This diagram illustrates a standard 3-node always-on availability group topology. The primary node handles the workload, while the secondary replicas remain idle, classified as passive. Arc continuously monitors the execution state of these passive nodes through its telemetry to ensure compliance with the licensing agreement. The definition of passive is absolute. Routing read intent queries to the secondary replica, running analytics, or adding a standalone read-write database outside the availability group violates the passive state. Arc dynamically detects this workload. It instantly converts the node status and triggers hourly billing. This strict definition of node state directly impacts how you execute routine patching and maintenance windows for always-on availability groups. Arc's automatic updates are entirely unaware of your availability groups. The system will not orchestrate a graceful failover of your databases before applying a patch. Your patching runbooks must be updated. Maintenance windows for the nodes must be deliberately staggered, ensuring secondary replicas are patched and rebooted first. Once the secondaries are back online, the database administrator must manually execute a failover of the primary node before its scheduled patch window begins. In a hybrid environment, Arc penalizes assumptions. Maintaining your free licensing and ensuring high uptime requires absolute node passivity and strictly staggered manual failovers. Before deploying, you must audit your estate against Arc's hard architectural blockers. The baseline operating system prerequisites support Windows Server 2000 R2 and newer, alongside major enterprise Linux distributions. This matrix shows the supported topologies. While older operating systems are supported, Arc enforces a strict topological constraint. Your SQL Server installations must be 64-bit architecture. There is also a firm naming limitation. If a single host contains multiple SQL instances, sharing the exact same instance name, the Arc SQL extension will fail to deploy entirely. For legacy shared storage topologies, such as failover cluster instances, Arc alters how you track management and billing. Arc views every node in a failover cluster instance as an individual physical entity. Agent health, telemetry, and ESU billing must be tracked at the physical node level, not as a single clustered unit. Bypassing these physical and architectural constraints guarantees an onboarding failure. A rigorous pre-deployment audit of your estate's architecture is a non-negotiable step. Azure Arc blurs the traditional lines between local database administration and cloud infrastructure management. If responsibilities are not clearly defined, deployments fail. This RACI matrix establishes the definitive operational boundary. The cloud admin team owns the infrastructure, configuring Azure RBAC, registering resource providers, and executing agent deployment. The DBA team owns the data, governing ESU activation, executing availability group failovers, and enforcing least privilege security. This strict delineation stops cloud admins from accidentally breaking localized high availability topologies and prevents DBAs from needing excessive, dangerous rights inside the Azure subscription. Azure Arc relies on existing local DBA expertise rather than replacing it. It functions as a management overlay that surfaces instance-level data to the cloud control plane. This automation removes the administrative overhead of manual inventory tracking and chaotic volume licensing audits, centralizing estate health into a single pane of glass. Mastering these operational boundaries allows the DBA team to transition from managing individual servers to governing the entire data estate using the same policy-driven model as their cloud counterparts.